Go.
Hello!
Hello, Mr. Area, are you alright?
Yeah.
Okay, so today we are going to talk about the binary tree. How can we check if two trees are the same, binary trees? Like,
We just check.
can you stand up, please?
Yeah.
So are these two binary trees the same? Are these two binary trees the same?
No.
Why is that?
Oh, because one has a 3 and one doesn't.
Okay, so the number of nodes are different, so they're definitely not equal, same binary tree, okay? How about these? Are they the same?
No.
Why is that?
The notes.
Sorry?
The notes on.
Sorry, which one? Come on.
This note.
This no, the values is different. So there are two things we need to check. The values, yeah? The values of the corresponding node should be the same. And the structure. The second thing is the structure, yeah? If the node, if a tree has a left tree and the other tree doesn't have a left tree, it's not equal, right? Eric? Yeah? Okay, so let's implement it using what kind of diagram can we use to implement to check if two trees are the same or not?
The notebook.
Sorry? No?
DFS.
Depth search or breadth search, both okay. So today we're going to use the depth search because it's easier to implement, okay? Let's say define and we're going to pass two parameters, yeah? A and B tree, okay?
A and B columns.
Okay, so what should we check at first?
We shall check the root first.
Yeah, the root of A and B, okay? So if one of them is empty, what happens?
And one of them is not.
Yeah.
False.
If both of them are empty.
True.
Okay, so first of all we need to check for if both trees are empty, yeah? If A is none and what?
B is none.
So yeah, what do you put here? B is none. What do you put here?
Or.
Or
And.
yeah, which one first?
And.
First. And now we return what?
Return.
If both are none, return what?
True.
Yeah, because empty equals empty, okay? And then one of them is empty, how can I write it? If at this point, what does it mean? Is A is, so not, both trees are not empty at the same time, right? Are we? So what should I do? If one of them is empty, yeah? If A is none, B is none, what should I put here?
Or.
Oh, and then return what?
Return false.
Yeah, because at this point, if A is none, then B is not none, right? If B is none, A is not none, right? Yeah? If a node compares to none, it's false, right? Okay, then at this point, what should we do? What should we check next?
We shall check the root.
The value, yeah?
Yeah.
So how can I write it? If what?
If
What? If what? Return false. Can you tell me? Yeah? If what? Return false. The A and B.
if
A what? The value. Yeah?
the value
What?
not equal
Not equal.
B the value column.
Yeah, later. And then now, so these three, at this point, A and B, the root is the same here, right? And what should I check? What should I check now?
The left binary tree and
The left and the right. And how can we check the left and right? What's the word? How can we check it? What? How can we check the left tree and the right tree? So what should we do now? What should we do?
we shall
Because the tree is recursion defined, yeah?
recursion.
Yeah, recursion. So we are calling this function to check the left and right. Yeah? How can we write it? Return something and something. Can you tell me? And then something involved the same, calling the same. Return what? Come on, if checking the root value.
A and
Yeah? We want to call the same value. Same what?
same
What? And then same what? Come on.
A
what?
the value
No, A the value is the value. We already checked. A the left, yeah, A the left. And
dot left and B dot right.
Huh? Why is right?
Left.
left. And what's
and
here?
same and A the right and B the right.
Okay. Okay, so you understand, yeah? We are recursion checking the left tree and the right tree.
Yeah.
We are checking, we are comparing both the left tree, yeah? We don't know how big the left tree is, but we're calling this recursion function to check the left tree, and then we check the right tree. Both needs to be the same, right? Yeah? Why this is working? Because, look, a tree,
Because
two trees are equal if the nodes are equal, and their left trees are equal, and then both their right trees are equal. Am I right? Does it make sense? Yeah? Is this is the back? What's the time complexity? If there are n nodes in A and m nodes in B, what's the time complexity?
and
Huh?
N plus N.
Do we need to check n and m if the node is one? There's one node in one tree and then a million node in the second tree. So how many nodes do we need to check?
How about how about minimum?
We're done minimum. Okay, so O
Minimum of N and M.
yeah, we're done because we just need to check the minimum. Yeah, if we don't need to check 1 million node, right? Because it will tell us false once the one tree is finished. Yeah, in the worst case. Yeah,
Okay.
yeah. What's the space complexity? Wow, it's the same. Yeah, is it the same?
Minimum.
Yeah, minimum. Minimum.
And
Because of what?
because of the recursion.
Recursion, and usually the computer
Stack.
maintains stack. Yeah, we're done. Yeah, stack. And we can implement it using the not the recursion. We can use the stack thingy, but it will be more complicated. We can talk about it maybe tomorrow or the day after tomorrow. Okay? Yeah. We maintain the stack by ourselves, but it will be a lot easier if we using the recursion because the computer generates the stack, maintain the stack for you when you do this function call. Yeah, return same, and the computer will put a stack, generate a stack, and call the function itself. Does it make sense? Yeah. Okay.
I can do it.
Yeah, if you understand, you can do it, of course.
Return.
Yes. Are you sure it's 8 on left or people? Yeah, because we check both the left tree and right tree. Yeah, B dot left. Yes. Okay. And then what? Yeah, it's n. N. What does n mean? Both needs to be true in order to be true.
Yeah.
Yeah.
Blah blah blah.
Yeah, that's it for today. Good job. Well done. Very well done. Say bye bye to people.